when I returned to Romania in 2014, I applied for this research grant, and 1 year later, I won it. Maybe you don't know, but in Romania, it's very, very difficult to get a research grant because the money is very, very small, very little. So we have many researchers fighting and competing one with each other to get this funding. And I was really lucky to get this funding. This is the summary of my presentation today. I will show you a part of the field investigation I have done together with my team, and then experimental tests, then some results comparison and some conclusions. This is the map of Romania. This is actually the Romanian zonation of the peak ground seismic acceleration. This is a part of our national seismic code. And you see here circled or highlighted some districts that we have done some field investigation because, so let me tell you a little bit of a history. My experience in these timber frame masonry structures is about 10 years. I have a PhD, which was, the thesis was made in Portugal on the Portuguese buildings, the Portuguese timber frame masonry buildings. And then I went to Japan and studied them further. I have many experiments from Japan actually on timber frame masonry structures. And then I realized that actually, because in many conferences I got this question, why you don't have any information about the Romanian timber frame masonry buildings? And that was actually a very good question. And that's why I think I won the first research grant, because nobody studied them before in Romania. So what I tried is to identify the structural system, because they are a little bit different than from the other countries. The timber frame masonry structures can be found all over the world. Even in China, the Chuandou system is similar to what I'm presenting today, the Romanian version. And actually it's a limited topic because few researchers are focusing on this. But these buildings are everywhere in the world, and they might be in countries which are seismic, but they can be also found in countries which are not seismic. And the structure is used for aesthetic reasons because it's beautiful. If you go to France, you will see in Strasbourg area, very beautiful city center with such buildings. In this presentation, I don't have the photos, but maybe I can show you later if you are interested. So going back to Romania, this is our map. And this is the seismic map, as I told you. You see here we have, this is very near to our main seismic source, which is called Vrancea. And it gives earthquakes with, well, this is the code map. And it's here 0.4 G. So this is the hot area, as I say. We made the investigation around this area to check the structures, the construction details of the structures with timber frames and some sort of infill, because I was not only focusing on the brick masonry, but also on mud infill or others. So we checked around, well, I had a very small team, like 2 students and 2 postdocs. And from the postdocs, only one actually worked. So the 2 students and I went on the field investigation. It was very interesting because I've never done a field investigation before. Can you hear me? or is it stuck?
Yes, I can hear you. No problem.
Okay.
I can hear you.
Okay.
But it shows that you make a pause. You make a pause. I can hear you. Yeah, I can hear you. No problem. Go on.
Okay.
I set my microphone, turned off my microphone because if there will be echo. So I.
Yes.
Yeah,
I'm
so
sorry. It's my first time I'm doing a presentation, and it feels like nobody's there, so it's very strange.
No problem. Yeah.
Okay. Thanks. So we have done the investigation on 129 houses. And these are the results. So I'm presenting them like type 1, 2, 3, and 4 according to the number that we found. So most of them were with timber skeleton and brick masonry infill. We call it Paiantă. So this is a Romanian name, like Ciondou. And then another type was with timber skeleton and wattle and dowel. We call it grădele. Then another type that we found was timber skeleton and earth with straw infill. And the last one with timber skeleton and strips applied at 45 degrees. I will show you all of them so you can understand what I'm talking about. This is the first one, the traditional house with timber skeleton and brick masonry infill. You can see the timber columns, timber diagonal elements, and there's also a beam here, and the brick masonry infill. Actually, the brick is made of mud, but I will tell you later. So these are some details about these houses. They're most spread. This type is mostly spread, and actually many specialists in the civil engineering area or the structural engineering area do not know that these houses are so widespread. So they are just telling that it's unreinforced masonry, but actually it's not. This is reinforced masonry. And this is a photo with the foundation. The stone foundations are very popular for this building. And this is a house, is the same house as this one and this one. This is from 1941. And it's very interesting, this house, because in 1940, there was an earthquake, a very big earthquake in Romania. And the previous house, there was a house here made of unreinforced masonry, so without the timber elements, and that one collapsed. And the owner rebuilt his house with the timber frame masonry structure. I will call it TFM structure just to have a short name. So I thought this story is very interesting and proving my point. So they are earthquake resistant, actually. They look bad, but they are earthquake resistant. Sorry, I'm coming back here. So after the 1940 earthquake, it also survived. It was built in 1941, and then our latest major earthquake was 1977, so 40 years ago. It survived very well, that earthquake, so no damage. And again, proving my point that they are earthquake resistant. This is another type of, this is another example of the same type, type 1. You see very clearly the timber skeleton and the brick masonry infill. Some of them don't have finishing, as you can see, but this is, I don't know why they don't have finishing. Maybe they just didn't have the money to make it, or they just thought it's beautiful like this. I'm not sure, but on the inside they have some sort of finishing. These are also some details, like the stone foundation. Here you have some, a little bit of retrofit work, but not very engineered. And another interesting detail is that the last layer of bricks is laid like this. We also don't know the reason, but we have seen it often. And another thing that I'd like you to notice is that the diagonals, so the bracings, these ones, are not connected to the upper joint. They're a little bit lower. This was an issue that is internationally researched, why the bracings are lower. And what I found from Romania is that actually it's for, how to say, constructive reasons. So when you start to build the house, you put the column here and then you support it with those diagonals. So initially the structure is not, the bracings are not meant to actually stiffen the house. They are just meant to support the column until the whole house is built. This is another close-up look with a similar building. You see again the diagonal. The connections of this type are usually cross-half joints. I will show you later some details what I mean. And mortise-tenon joints. Also, I will show you later in the experiment. And some connections are made just with nails. For example, this one between the bracing and the column, just simple nails, not even screwed nails, just plain nails. This is another example. Sometimes the bracings are not very well applied. For example, sometimes they just stop for no reason, and sometimes they're not connected to the column. As you see here, they are stopped a little bit earlier, just connected to the bottom beam. So many details which are not correct from the point of view of the engineering. And this is a house which I found in an old archive. It was an architectural archive, and they said that this is the classical timber frame masonry house in Romania. But actually, I've never found this type of house with such type of foundation, like wood piles. I only found the foundations made by stone. So I'm not sure where they found this house. And also, you see here that the diagonals are stopped in the joint at the upper part. So what I found in the field investigation was not this house. So I thought to myself, okay, I have to make a new guideline to present my results and to confront them with the architects that studied them. And this is a drawing made by one of my friends, architect, with one of the houses that we found. And this is the second type that we found. But the photos for this second type are not very good because we cannot see very well the details. But I think you may have heard of wattle and daub, like some branches. So we have the timber columns here, the bracings, and some branches. But the bracing actually is not typical for this structure. In this example, the bracing exists, but for I don't understand Chinese, but anyway. These are branches which are connected with nails by the main structure.
No problem. Don't worry. No problem. Some other people maybe talking about other things.
Okay.
So this is a problem. Sometimes if their microphone is not turned off, they will have such a kind of problem. That's why
yes,
I turn off my
You can hear
microphone.
The children. Yes, no problem, no problem. And the actual infill, so you can see here some mud, is just mud with straw, so mixed with straw and just applied on the wall. This is another example of this type, the second type. As you see, the photos that I'm showing are with very old houses. Many of them are abandoned. and actually the ones that are well maintained, you cannot see the structure. You can just see the finishing. So that's why I'm showing you only photos with old, very old houses looking like abandoned. This is a close-up look with the same house that I showed you earlier. You can see here the Lanzhou infill, as I told you, some tree branches with mud and straw infill, the timber columns, and the foundation usually is made of stone. You see here we have no braces. This is a hybrid example. It's actually type 2. You see this part is type 2, and from here it's type 1. So I guess after the 1977 earthquake, this house was retrofitted with this style, the first type of structure. This is also a photo from that archive that I found, the architectural one, and you see the columns are supported with some small braces just for constructive reasons. And these are the branches attached to the columns by small nails. And here they apply the infill. You see, they have no braces in the final structure. This is another type, type 3, just a timber skeleton with some straw infill. You see here we have the columns. We also have some braces, usually, and some exterior strips applied on the structure. And from here, they input the infill. Infill is just with mud and straw mixed together. This is another example of the same one. You see here, this house is pretty new. It has a new roof. So I guess people are still building with this type of structure. This is a very poor example of the same type. This house is, well, the owners are very poor. You can see they have no windows. They have a TV though, and no functional roof. But the structure has bracings, you see here. And please remember the exterior strips. For the same house, we were shocked to see that there is no foundation, and the details are very poor, like the bottom beam joint here seems to lack nails or clamps, which actually join the two pieces together. Another type, and I think the last type I will show you today, is the traditional house with timber skeleton and the strips, which you have seen earlier, laid horizontally. In this example, the strips are laid at 45 degrees. Sorry. For this example, I don't have more photos. As I mentioned, some of the houses were covered. Well, I have more examples, but I don't have photos. And the infill is the same as the previous one with mud and straw. I will now show you the experimental tests that we have done in this project. So we had two main experimental campaigns. The first one is with 4 walls. So we reproduced, we took an example of the house, because you may have seen that the details vary a lot, even between two houses from the same type. So we just decided, okay, we just take this house and we reproduce the details that we find in it in the laboratory. Because our budget was limited and we couldn't make many tests to check all the details that we have found. And we decided this layout. So first we have this wall, we call this S1. We have the beams, the columns, and the bracings. You can see the bracing is stopped lower than the upper joint. For all the walls, the connections are, the bottom ones, mortise and tenon, and the upper ones are cross-halved. This S2 was with the diagonal, so was identical with this one, with the first one, sorry. And the only difference is the position of the diagonal. Then the third one has the same internal structure as this one. So the diagonal is up, is connected with the beam and the column. And the infill is mud with straw and with the horizontal strips applied on the both faces of the walls or of the wall. And the last specimen, S4, was the one with the wattle and dowel. So we have, well, the same timber frame we have, except we don't have diagonals here, we don't have bracings, and we have the branches which are filled with mud and straw. In the same project, I also did a second campaign, a very small one, or actually just one wall, just to compare my test. This one was made in my university in Romania, just to compare it with the test that I have conducted in Tokyo Institute of Technology in Japan. Because this experiment was very, how to say, we had a problem with the vertical axis, which was applied through tie rods like this. You can see here the tie rods. And many specialists, many reviewers for my papers said that this is not a correct way to apply the actual load, the vertical load, because actually it increased with the amplitude of the experiment. So when the top displacement was large, also this value of the vertical force was also increased. So I did the experiment again in Romania, where we have a facility which was donated by JICA, by Japan, which can test walls for about 3 per 3 meters height and length. So this is almost 3 and 3 meters high. And we have a pantograph system, and we can control the vertical force applied on the wall. This is the setup. This is what I'm mentioning. This is the reaction frame that we use. This is the pantograph system. We have 2 horizontal jacks and 1 vertical jack. And this is the specimen and the measurement system. We measured the displacement at the bottom of the connections, the top displacement also. This is the loading protocol that we used. We used the Curie-Caltech loading protocol to compare it with my previous experiments. Another choice was the European, the Eurocode loading protocol. But since I wanted it to be consistent, to have a comparison with my previous research, I used this one. And the first experiment that I have done, these yellow sheets are actually just because this was the first experiment I was conducting in Romania. So I don't know. I was not very sure of what was about to happen. So I was just, okay, I put them there in case that anything happens, and I will have some safety, safety part. Okay, this is the vertical load. We applied it, as you see here, if you watch closely, we applied it on the columns with some steel plates. The total vertical load, which was controlled manually, but it was set as constant, was 26 kilonewtons. Then we had a wire transducer here to measure the top displacement. We had a transducer here and here to measure the relative displacement of the connection, of the bottom connection, and also some transducers to measure the slippage of the bottom beam from the reaction plate. these are the details of this specimen. And what I want to show you is the cross-halved connection that I was mentioning before. So this is cross-halved or half-lap. You can find it in the literature with both names. And we used it here at the upper part. And this is the mortise-tenon joint connection, which we used in the bottom part. As I mentioned before, the specimen was about 3 meters length and just 2.4 meters high. This is the deformed specimen at our last cycle. Actually, the wall was not broken, but because this reaction frame is made especially for reinforced concrete frames and specimens, the stroke is not so much for timber walls. So we just had 12 centimeters to the right and 12 centimeters to the left. But we could get this hysteresis. And you see here, I'm mentioning that actually this is not the failure of the wall, but it's just the stroke finishing, the stroke of the jacks that we use. You can see the maximum recorded shear angle was about 0.05. And the maximum capacity was about 28 kilonewtons. Some damages from this experiment. We had some bending crack. This is the upper connection. You can see it's a cross-half connection. We had big gaps in the connections and some small compression perpendicular to grain also in this connection. A very specific damage type is the detachment of the infills from the timber frame, which will happen even from the beginning of the experiment. And this makes the infills very vulnerable to out-of-plane action, which we did not study in this research grant. This is the bottom connection. You can see here some cracks in the masonry. Here we have a little uplift, but not so significant. I also have to mention here that even from the execution point, we had many gaps in the connections because we had a company which was not specialized in traditional structures that built our walls. We couldn't find any specialized company to build our walls, so we just took one company and we trained them to make the connections, but this is what we got. And this is actually the second time they built these walls, because in the first time they were not good. But actually this is the reality from the field, so it was okay for us. Again, the bottom connection, you see, this was the initial, we marked the initial position. You see such deformation of the connection and the gap here from the uplift. But actually the uplift is not so significant. This is the upper connection, and you see here some displacement of the column, but also initially I think it was also displaced. So the actual displacement is not very important. You see here very well the out-of-plane behavior of the masonry infill. This is my hand, so you can understand that the panels are very easily falling out. And this is the bottom joint connection, the bottom connection from the middle bottom connection. You see how braces are detaching. You see the nails. But actually, this is let's say the right cycle, and when the wall goes back and goes to the left on the negative cycle, then this brace goes back and nothing happens. So for example, this one. So it's exactly the same as in the beginning. Okay, this is the second specimen. As I mentioned, the first one was with the lower brace, and this is with the upper brace, which connects directly into the beam and the column. The rest of the elements are the same. So this is the wall, and this is the deformed wall after the test. This is the hysteresis. If you remember earlier, the first one had a maximum capacity of 28 kilonewtons. Well, this one was 30, so not very different. And the same 0.05 radians, the shear angle. Some damages I will present now. Actually, the uplift in the connections are really significant, especially when compared to the previous one. This is the middle bottom connection. You can see the tenon. In the previous one, you couldn't see this. You can see the very big crack in the masonry. Again, the same connection on the other side, the crack in the masonry. In the upper joints, you can see the uplift here, and out of plane of the masonry infill. And this, again, the crack in the masonry. Okay. And this is the third specimen, as I mentioned. Well, the timber structure, the main timber structure is the same as as for the specimens before. The only difference is that the infill is mud with straw, and the horizontal strips, which are applied on both faces of the wall. This is the wall before the test, and this is the wall after the test. So you can only see some damages along the diagonals, along the bracings. And this is an upper connection, some very, very small compression perpendicular to grain. This is the uplift in a bottom connection. It's also significant as the previous one. Some cracks in the masonry you can see here. This uplift of the detachment of the bracing from the beam column joint is also significant. And this is the hysteresis. It's similar to the one before. And the last wall that we tested from this series is the one with wattle and dowel. Again, the timber frame was the same, but the bracings are missing. And the infill, of course, is wood branches and mud infill. This is the wall before the test, and this is the wall after the test. Well, this wall actually had no damage. So that's why I think I don't have, I have small photos with, I have some photos with damages. This is the hysteresis. You see the maximum horizontal load recorded was 15 kilonewtons. Well, here, half of the one recorded for the previous specimens, and very high ductility at 0.06 shear angle, 0.06 radians, you see. And some small damages, but actually they're insignificant. Some small compression perpendicular to grain here, and almost no uplift here in the bottom connection. Well, and the infill, you cannot really tell if it's cracked or not. Our observations were that initially, even from the beginning of the test, the infill was cracked, but it was cracked from the drying procedure, not from any movement or deformation of the actual wall. This is the middle bottom connection. You see it has no uplift. Here there is very small uplift between the upper beam and the column. and, well, cracks in the infill, but you cannot really tell if it's initial or not. If you notice, there is no falling of the mud mortar around here, just very, very little, which means maybe not so cracked after the test. Some small detachment of the infill panels could be observed during this test. And I will show you now some comparison between all these tests. So first of all, between the first two, where the parameter was just the position of the diagonal. So the one with the lower diagonal is the black line. You see, actually, initial stiffness is much lower than for the other wall, but the maximum capacity is similar. So even if I think the diagonal starts to work, the brace starts to work later in the experiment. So when it starts to work, then it gives similar horizontal load. Some comparison between the damping ratios, stiffness degradation, and energy dissipation. Again, the black line is the one with the lower diagonal. You see here, well, we also had a small problem in the first test because it was the first test. So some differences like this one makes not much sense, but it's from the experimental setup. I will not go into details, but anyway, we had some problems in the test, so not in the wall. Nothing happened here. So you can see a little bit higher damping ratio for the wall with the lower diagonal. In the stiffness, you can see smaller stiffness for the lower diagonal. And for the energy dissipation, I think it's similar. We have some seismic characterization parameters for both walls, S1 and S2. I use 3 methods to see which one is better for such a wall. For example, I use the Eurocode, and it has 2 methods of well, bilinearization, and I also use the ASTM. So these here are presented the bilinearization methods. I have the hysteresis, then I try to make a bilinear curve from which I get the initial stiffness and the ductility and these parameters here, for example. So I can compare all walls because there are many tests being done around the world, and we cannot actually, because the experimental setup is different, and we use this type of bilinearization to be able to compare them. But as you see here, for example, for, let's say, initial stiffness, right? Depending on the methods, they are kind of different, see? So if you use method B in the Eurocode, is half the one obtained from method A. Anyway, I evaluate them and check which one is better. This is the curves that I obtained. These are from the positive loading, and these are from the negative loading. And the dash line is the experiment, and these lines are the ones corresponding to each method that I use. And you see here, the best match is the Eurocode method A, but on the negative loading, well, the best match would be the method B. So it was very confusing to decide actually which method is better. This is for S2. Again, here the B method is, well, better for the initial stiffness maybe, but for the maximum load is not better. And you see here method A. Actually, the method A was the winning but just comparing everything that I obtained, I guess method A is more suitable for such wall than the other ones. And I have here a comparison of bilinearization method A, which was used for many other types of walls. And first two are these ones that I showed you. And just look at the ductility factor, which is 14 and 13. And I compared it with, I compared the walls with the other, both traditionals and new types of walls, like joint CLT wall. You see, the ductility ratio is much smaller than the ones obtained from these traditional Romanian. I also compared it with the Japanese test that I have done, which is also much smaller than the traditional Romanian ones. And the Pombalinho, the Portuguese wall, is also smaller. So I was very surprised to see that actually the traditional Romanian houses are more ductile. So I compared the envelope curves for all four specimens. You see, this is S2 and this is S4. So S2 and this, sorry, I think it's, anyway, the most similar envelope curve is this one with this one, because the actual internal structure is the same. So that the diagonal is here, is also connected here, so they are similar. And this is the one with no diagonals, this one. This one is this one. So you see, it's half the capacity that the others have. And for S1, the one with the lower diagonal, so it has a lower stiffness than the others, these two, but it has a maximum capacity similar with the others. Then I compared the energy dissipation of these three walls. So I removed the one with the upper diagonal because actually this is the real version of the traditional house. And I compared here sorry. So this one dissipated less energy than the other two. This is the green line. And I also calculated some seismic coefficients, like depending on the maximum strength obtained by the static test, divided with the vertical force applied. So actually, these are the results. So S2 and S4 are having the higher coefficients. Again, I mentioned that these two, S2 and S4, have the diagonal directly connected to the beam column joint. And this is the second part of the experimental program. So this is the Tokyo Tech test, and this is the one in my university in Romania. And this is the envelope comparison. So the result is very different. It's almost half, right? More than twice stronger. So many people say that, okay, the test setup is not the same and the materials are not the same because I could not use the Japanese brick and the Japanese timber. So these factors are also influencing the behavior, but still, I think the Romanian test is closer to the reality. In any way, the Japanese test was very interesting because it shows, actually, it opens some ideas about strengthening of such buildings. You can see we got more than twice maximum capacity for the same type of structure. And some conclusions of this first project. For the first time in Romania, experimental tests were performed on wall specimens, executed as the existing traditional houses. The mud brick infill of S1 showed that it is cracked even from the beginning, this being according to the real situation when clay mud cracks immediately after the application, after it gets dry. For this specimen, significant out-of-plane behavior was observed for the infill, as I showed you in the photo. For the Lanzhou specimen, it showed half the maximum strength obtained for the other two specimens. The other three specimens, sorry. The traditional version of this house contains no bracings, but sometimes in the existing houses there are bracings, so it's better for the houses with bracings, but yeah. And for the S3, not many damages were observed, except cracks in the mud infill, especially along the timber bracing. For all the specimens, significant deformation capacity could be observed. Oh, sorry. And overall, the behavior of the houses, the traditional houses, was good. Now there is a lot of work ahead. For example, from this study, we have calibrated a shear spring model, which I'm not presenting now because it's also much longer to explain. This shear spring model, well, many people from the technical committees of the ministry contacted me that I should make this model, well, I should simplify it and input it into the guidelines, into the seismic code of Romania. But for this, I have to make more research. So just from 5 tests is not enough. So, but this project was the beginning of the research on the topic of Romanian traditional houses. And now many people are interested in strengthening techniques, which I also researched in Japan. But I think some of you, which attended my presentations while I was in Lanzhou, I think you have seen some aramid fiber reinforcement research. So I just show here the acknowledgement, the grant from the National Romanian Authority for Scientific Research. And we also have 2 papers published about this project. They are open access, so you can just type my name on the internet and engineering structures. The journal is engineering structures, and you can find those papers. And if you have questions, I'm here. And I would also like to thank Professor Du for this opportunity. It is very nice